Welcome to this segment of the Math Coach. Today we're going to take a close look at some of the review problems from unit number 5, trigonometric ratios. Although this unit is the most challenging in this course, you'll need a good grasp of these concepts in order to continue your math journey in grade 12. I can't wait to get started. Let's take a look at number 5a on page 318. And number 5a, this is from the sine law, the ambiguous case. It gives us these measurements for little a, side length little b, and angle A is 35. It says find all appropriate and sketch all appropriate triangles given this information. So what I'm going to actually do, and this is what I always do, I go to draw a triangle, and I always draw a triangle pretty much the same way every time. And remember, this is just theoretical math. So this is triangle ABC. And we know that little a, which is across from big A, is 7.2 millimeters. Little b, which is across from big B, is 9.3 millimeters. And angle big A is 35 degrees. So this is the information that we're given. Now, we're asked to find all side lengths and all angles of this triangle with these measurements. So when you go to do this, the way that it's set up, we have, two side lengths, okay? So we do have two side lengths here, two side lengths. And we're also given an angle that is opposite one of the side lengths. When we're given a situation like this, we know when we have two side lengths and an angle that's opposite one of the side lengths, we're going to use the sine law. So how are we going to use the sine law? And of course, we're using the sine law, not trig ratios, not SOHCAHTOA, because there's no 90 degrees. So the way we'd set up this sine law is sine of big A over little a is equal to sine of big B over little b, and is equal to sine C over little c. But I don't have C or little c, so I'm not going to worry about that right now. Now, if I plug in the data that I have here, I'm going to have sine of big A, which is 35, all over little a, which is 7.2, equals sine of big B, which I don't have, all over little b, which is 9.3. Now I set this up with the big B on the top of the equation because I'm trying to find an angle. So I've set up the sine law this way. Now, when I cross multiply the 9.3, I get this. And when I simplify the left side there, I'm going to get that sine B is equal to this long number over here. And of course, I'm going to keep all the decimal places for now. And when I bring sine to the other side, it will be sine inverse. I'm not going to retype this whole thing here. I'm just going to write sine inverse of that answer, which is already on my calculator. And when I round this to the nearest degree, I get 48 degrees. I mean, this would be pretty good if this was grade 10 math, but this year we're actually figuring out some actual real life things that occur with these sines and coses and all this sort of stuff in the terminal arm. And if you remember from section 5.4, if you take a look at this line right here, sine B is equal to this positive, it is a positive number. We have to remember that when we are talking about sine of an angle is positive, according to the cast rule, there are two places that sine is positive. Sine is positive in quadrant number 1, and sine is also positive in quadrant number 2. Remember that in quadrant number 1, you're going to have acute angles, and in quadrant number 2, you're going to have obtuse angles. Both types of angles do occur in triangles. So you actually have two answers, like in 5.4, for this line right here, sine of B is equal to a positive number. You actually have two answers. Now, is 48 one of the answers? Yes, 48 is the answer in quadrant number 1. Now, how do you get the answer in quadrant number 2? I mean, we could draw it out, but in order to be in quadrant number 2, like this, the 48 would be on this side. And so to fix the other, I guess, answer for B, we would have 180 minus 48, and the other answer for B would be 132. So these are my two answers, my possible answers for B. Now I have to see if both answers make sense in the original triangle. So the original triangle has these measurements right here. Okay, so the first option is that B is 48 degrees. So I'll write B is 48 degrees. All right, so that's the first option, that B is 48 degrees. The second option is actually that B is 132 degrees. Does that make sense with the given measurements up here? So let's draw that out. So if we draw it out, the second option can look like this triangle here. So this triangle here, right here, has an obtuse angle for B. And remember, the second option for B was 132 degrees. And that still makes sense in the triangle because over here we have 35. And 35 plus 132 is only 167 degrees so far. And so we could figure out what C is, because we know all of the angles in a triangle add up to 180 degrees. So there are actually two different triangles that can be constructed with these measurements. The first triangle would look like this, and I'll let you finish this on your own. How would you finish that on your own? Well, you got to find, obviously, angle C first, because you know all angles add up to 180 degrees, and then you could find little c on your own. And the other option is you could have the triangle look like this, where you have the angle B 132. So again, I will have you finish this problem by figuring out angle C first and then little c using the sine law as well. Let's take a look at page 318, same question, number 5, but C. So again, it's asking me to construct as many triangles as possible with these given measurements. So I'm constructing a triangle ABC. Now it's telling me that angle A is 33 degrees. Little a across from big A is 1.3. This is all in centimeters. And big B across from little b is 2.8. So little b is 2.8. And so it's asking me to solve for this. Again, there's no 90 degrees. So I can't use SOHCAHTOA. What am I given? I'm given these two side lengths, and I'm given an angle that is opposite one of the side lengths. That is set up for me to find or to use the sine law. I have big A and little a. I have little b, so I'm going to find big B next. So the way I'm going to set this up is sine A all over little a is equal to sine B all over little b. And I'm not going to worry about the sine C and little c because I'm going to just find big B. I can only find one thing at a time. So plugging in all these numbers into the right spots, I should get this here. And then I'm going to cross multiply the 2.8. And then I will simplify the left side. So on this side, I'll leave it with sine B. And when I do all this, I get this long decimal answer right here. Sine B equals all this. Remember, again, when you're dealing with the sine law, and you know that the cast rule has two places where sine is positive. The two places are in quadrant 1, the acute angles, and in quadrant 2, the obtuse angles. So you have to take into consideration both answers and see if both answers work. Well, when you bring sine to the other side, so I'm going to bring sine to the other side, opposite of sine is sine inverse of this thing, which I'll just call answer. I'm not going to write that out again. And when I do sine inverse of that thing, I actually get an error on my calculator. So if I get an error on my calculator, that means there are no answers for B. So there are no answers. What does that mean? If there are no answers for B, then that means that it is impossible It's impossible. You can try doing this with a protractor and a ruler. It is impossible to construct this triangle. Impossible. You cannot construct a triangle with these measurements here. So on the same page, we have yet another question that asks us to construct all possible triangles with these measurements. And so I'm going to call this triangle, since I'm dealing with A's, probably B's, I would say. So A, B, C. If I construct this triangle, I'm obviously not drawing it to scale here. I always kind of draw a triangle that looks the same on all sides. However, using theoretical math, it's telling me that this is 36 degrees. Across from angle A is little a, which is 5.0. And this is in centimeters. And across from big C is little c, which is 8.5 centimeters. Now, how am I going to solve this triangle here? Well, if I take a look at the triangle, there's no 90 degrees here. So the only way I'm going to solve this, if I'm given two side lengths and I'm given an angle that is opposite one of the side lengths, clearly I'm going to use the sine law. In this case, I'm going to use the sine law. I have big A and little a, and I have little c, so I'm going to find big C next. So the way I would set up this sine law is I would set it up as, since I'm finding an angle, I put the angles at the top. Sine A over little a is equal to sine C all over little c. Plugging in all the appropriate numbers, I get this here. And of course, I'm going to cross multiply the 8.5. And then after cross multiplying, I'm going to leave the sine C alone here, and I'm going to simplify the left-hand side. So I get sine C equals this positive number. So it's very important that we always look at this part of the sine law, because in the sine law, we have to remember there are two places that sine is positive. One answer will be in quadrant 1. The second answer has to be in quadrant 2. Now, not always do both answers make sense, but we still have to show our work to figure out both answers. So when I go to figure out C, obviously the first answer that I'm going to get here on my calculator will be the acute answer. So I'm going to do sine inverse of that 0.9923, so forth. And when I round that properly to the nearest degree, I get that C is 88 degrees. So that is my first answer. That would be the answer in the first quadrant. Okay, but how about the answer in the second quadrant? We have to remember that the second answer may be in the second quadrant. Okay, and how do I come up with the answer in the second quadrant? Well, just remember that the 88, in order to get into the second quadrant, the 88 would be the identical triangle inside the second quadrant there. If you take a look back at my 5.4 lesson and explanations of many of the problems there, you'll know what I'm talking about. And to fix the other answer, I should get C is equal to 180 minus 88. And so I get that C is equal to 92 degrees as my second answer. Now, if I take a look, does C equals 88 work in this triangle? And the answer is yes. And does C equals 92 work in that triangle? And the answer is also yes. I mean, sometimes one of these answers is just too big in order to work in the triangle. And so you would only have one possible triangle. But in this instance, you have two possible answers for C. And therefore, you'd have two different triangles that you're constructing and two different answers for B and so forth. If we look at question 7, page 333, it talks about Romeo serenading Juliet while she's on the balcony. Now, if this is Juliet at the balcony and I draw a line straight down, we got to remember that they have it drawn here. Romeo, this is like Romeo coming out of the page. Romeo's on the ground and Juliet, this line right here, is straight up and down. Romeo's horizontal. This is actually 90 degrees here. That's coming out of the page, okay? And we know that Romeo is looking up at an angle of elevation of 20 degrees. So that's Romeo looking up at an angle of 20 degrees right there. We also have this other point P for Paris. And also Paris is on the ground, but obviously on the other side of Juliet. Again, Paris is on the ground is horizontal, and this line here is vertical. So this is also 90 degrees, but it's coming out of the page. It says the angle of elevation that Paris looks at Juliet is actually 18 degrees. Now, they were nice enough to give you the picture, but it's very important that we understand what the picture is. Then there's a bird's eye view of a triangle. Okay, so there's also a triangle where all three sides are on the ground. There's the base right here of the balcony. There's Romeo who's on the ground, and there's also Paris who's on the ground. So this line joining the base to Romeo, that's on the ground, joining the base to Paris, that's also on the ground, and the line joining Romeo to Paris is also on the ground. That red triangle is actually on the ground, but that black triangle is meant to be coming out of the screen, and same with the blue triangle. And they tell you that the distance between Romeo and Paris is 100 meters. It's asking us to find how high Juliet is. How high is the balcony? So this line is called H. Okay, I put it in green, but notice that is a common line between the black triangle and the blue triangle. So that is what we're trying to figure it out. Now, this is quite, when you look at this firsthand, there's no other measurement given to us. If I redraw the blue triangle like this, and I actually talk about the measurements given, I mean, they told us that this is 90. Well, they didn't tell us that. We know that Paris is on the ground, and so is the bottom of the balcony. And we know that Juliet, this is straight up and down, so that's a vertical line. So we know that's a 90-degree angle. We are trying to find H, and all we're given is that this is 18 degrees. Now, that's impossible to figure out H with just this measurement. It would have been nice if they gave us, let's say, this measurement right here. If they told us this measurement right here, which I'll call X because I have no idea what it is, but if they gave us that measurement there, we would be, no problem, we'd find H using, obviously, trig ratios. So I'm going to label that as X, okay? We don't know what this measurement is, but if they did give us this measurement, we could solve that problem right away. Similarly, I'll draw the black triangle where there's Juliet, there's the base of the balcony, and there's Romeo here. Now, they didn't give us this was 90 degrees, but we know that because Romeo is on the ground, and that's horizontal to the base, and we know that this line is straight up and down. They're giving us that this is 20 degrees here, and we are trying to find this height. It is impossible for us to find this height. I mean, there's no way we could find this with no other measurement. However, if they gave us, let's say, this measurement from here to here, which I will call Y, different from the X, but if I call that Y, if I had that measurement, this would be no problem because I would just use SOHCAHTOA, trig ratios. So I'm going to label this as Y, this measurement from the base to Romeo. So how does this help us? Well, let's take a look at both triangles and let's try to come up with trig ratios. Now, I'm going to take a look at the first triangle that is in black, okay? And coming up with the trig ratio here that deals with all the stuff I'm given. I mean, it's 90 degrees, so I can use SOHCAHTOA, otherwise known as trig ratios. I'm given this angle here, trying to find that, and that is the opposite, okay? And obviously, I have labeled this side as Y, and this Y would be the adjacent, okay? And what relates opposite and adjacent? Well, opposite and adjacent are related by tan. We know that tan of the angle that you're given is equal to opposite over adjacent, okay? And if we fill in the blanks here, we get that tan 20 is equal to H over Y. I'm not sure how that's going to help us, but let's do the same thing for the blue triangle. And once again, we know that the blue triangle is 90 degrees, so I can use SOHCAHTOA. I'm given 18 degrees. I am trying to find this h, which is opposite of the 18 degrees. And I have no idea what this x is, but that is the adjacent side. And so if I come up with a trig ratio for opposite and adjacent, it's 10. And so I get tan of 18 is equal to h over x. So that's what I have thus far. Now, let's take a look at the last triangle. The last triangle, the red triangle, looks like this. And it's a bird's eye view. And we have that this is 100 meters. We have that this side length over here is y. And we have that this side length over here is x. Now, there's one important piece of information we forgot to read. So this is Paris here, and we know that this over here is Romeo, and we know that this is the base of that tower. Now, it clearly states that Romeo, if you look back, it says Romeo is facing north. So Romeo's direction that he's facing this way, and he is facing north. Remember, our directions, I remember as never eat shredded wheat. That's how I've come to know this, so never eat shredded wheat. So he is facing north. Now, we also know that Paris is facing, it says, Juliet's other suitor Paris is observing the situation facing west. So the way he's facing is west. So in actuality, if one person is facing north, and we'll draw this on regular direction. So if one person is facing north like this, and one person is facing west, that's this way, west, that would meet north and west. If you're facing north and west like that, that is going to meet at 90 degrees. So that is actually a 90-degree triangle on the ground that we forgot to speak about here. So it's very important that we caught that with the north and the west. Otherwise, we couldn't continue this problem. Now, I have actually erased everything because I wanted some room for equations. But now this third triangle that I'm dealing with here, we know is a 90-degree triangle. And if we're taking a look at what we're given that this is 100 meters. I mean, we don't know what x is, but and we don't know what y is, but somehow, some way, this triangle relates all three sides. The only way you can relate all three sides of the triangle is through what is called the Pythagorean theorem, because we know that is a 90-degree triangle. Pythagorean theorem states that hypotenuse squared is equal to side 1 squared plus side 2 squared. Okay, and I'm actually going to figure out what y is equal to, and I'm going to do that with using this formula here. Okay, because we do have this formula here, and if I actually solve for y, so if I cross multiply the y and at the same time divide out the tan of 20, I get that y is the exact same as h divided by the tan of 20. So instead of writing y, I can write this thing. Y is equal to h divided by the tan of 20. Okay? And then I'm going to do the same thing for my x. I'm going to solve for x using this equation over here. And if I cross multiply the x and divide out the tan 18, I get that x is equal to h all over the tan of 18. And so instead of writing x, I can just write that x is equal to h divided by the tan of 18. Okay, and so if I continue this formula up here, c squared is equal to a squared plus b squared. I know that c is going to be my hypotenuse, so c is going to be the 100 squared, okay, plus A, we'll call side A this one, and we'll call side B this one. That doesn't really matter which one you call side A and side B. However, so A squared is going to be that side, which is called H all over 10 of 20 all squared, plus I have my B, which is H all over 10 of 18, and that's all squared. And so now I could actually solve this problem. So when I do 100 squared, I get 10,000. This equals, now squaring both top and bottom of that number, so h squared at the top is h squared, and then if I do tan of 20 squared, all I would do is tan of 20, and then I would actually square that, and I should get 0.132474331. I mean, this is one way of doing it. Another way of doing it would be to actually leave the bottom as tan squared 20 and do the same to the second fraction, and then factor out an h squared from both. But I'll do it this way here. So I'm going to square both top and bottom here, again squaring the h, and then doing tan of 18 and squaring that, I get 0.105572809. How does this help me? Remember that there is a 1 in front of the h squared here. So I could actually do 1 divided by that number here and write that out in front of the h squared. So 1 divided by that entire number gives me 7.548632195 h squared. I'm not going to round any of that because I want to keep all the decimals. And I'll do the same over here because this is a 1 in front of the h squared, so I'll do 1 divided by that decimal there. And it leaves me with this long decimal, 9.472135955 h squared. And so I can add those two h squareds together because that many h squareds, so this 7.54 blah 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 h squared plus this many h squareds is equal to 17.020768158 h squareds. Again, this is not the best way of doing it. The best way of doing it would be when you get to this line here, if you square both top and bottom, you could actually factor out an h squared from both and continue on algebraically from there, but we will continue this. Now, obviously, to isolate for h, I would have to divide both sides by this 17.0, the rest of this, which eliminates it from this side, leaving this with h squared is equal to, doing this division, I get 587.5175498. And to get rid of the square, I will take the square root of both sides, leaving me with h is equal to 24.23. So if you round it to the nearest meter, which is what they're asking, you get 24 meters. It was actually a pretty tough problem because you'd have to somehow, some way, get all of the triangles and compare them somehow together like I did. So let's take a look at page 334, number 11. It says Bert wants to calculate the height of a tree on the opposite side of the riverbank. So what he does to do this, he lays out a baseline 80 meters long and measures the angle as shown on the left. So what he does is he plants a stake somewhere around here and a stake somewhere around here, and he measures that. That is 80 meters long. Okay. And then he takes out his protractor or whatever he's calculating, and he looks at a straight line. Now this is obviously, he doesn't go across the river, but he just eyeballs it and he sees a straight line to the tree. and he notices that this straight line forms 85 degrees with his line that he has on this side of the river. He does the same. He stands over at the other end point and looks straight at the bottom of the tree, and he realizes that this is 30 degrees, okay, with his protractor. So he's done those measurements there. Now we have to realize that this is a bird's eye view of the triangle. This triangle, this point at the base of the tree, the point on the left, and the point on the right, all those points are on the ground. They're all horizontal lines. So this is a bird's eye view of this triangle. Of course, we could find way more things about this triangle because we have that this side is 80 meters. We have 85 degrees, 30 degrees, and we could even figure out this if we wanted to. Not an issue because all of the angles add up to 180. Now, he wants to find the height of the tree. So what do we know about this line here? I'll draw it in red. This line here is a line that is on the ground, okay? Or on the water, or whatever you want to call it, but this is ground level, this line. So this line here, and this line here, right here, the tree line is a vertical line. So this is a vertical line right here. And we know that this other line here is a horizontal line. So technically, that line there, actually, those two lines form a 90-degree triangle that pops out of the page. It's kind of hard to draw a three-dimensional object on a two-dimensional piece of paper. However, this line that goes straight up and down, this line that's a horizontal line, they meet at 90 degrees. So we know that this is the height of the tree. And we also can connect the top of this red line with the bottom of this stake right here, okay? And if you draw that and look at it on a side view, side profile, you have a 90-degree triangle that looks like this. It also says that the angle of elevation from A to the top, okay, so this was, remember, point A. So from point A to the top of the tree, that angle of elevation is 28 degrees. Okay, so this is 28 degrees. So we have a 90-degree triangle where we have a 28 degrees right here. And we'd need another measurement on this red triangle in order for us to figure out the height of that tree. Now that shouldn't be a problem because this right here, this line right here, we can call that line, let's say, well, if this is called big B, we can call that little b, for the little b to do with this black triangle here, okay? So we're looking at the black triangle. So that is the base of the red triangle, but it's also a bird's eye view of that black triangle. So this is actually little b. So it asks us, can Bert figure out the height of this tree? And the answer is yes, because what he's going to do is he's going to use the black triangle first, right? He has the black triangle and he could set up a sine ratio to figure out, use the sine law to figure out what this measurement b is equal to. The first thing he would do, obviously, is figure out this angle right here. We could figure out that angle pretty simple. I mean, I would call this point over here, I don't know, T for tree, or even C because it's triangle ABC. And if you wanted to figure out this angle, that angle C is going to be equal to 180 minus 85 minus 30, which leaves us with 65 degrees. Okay, so we also know that this is 65. Now, if that's 65 right there, then we can also figure out what little b is equal to, because we could set up the sine law. The sine law for triangle ABC, if you're trying to find little b, remember, we have little b, we're trying to find little b, and we have big B, okay? We have little c, and we have big C. So we could set up the sine law in this manner. We would set it up like this: little b over sine of big B, since I'm trying to find one of the side lengths, I'll put the side length on the top, is equal to little c over sine of big C. No need to incorporate a because we have no need for little a. Solving this by first plugging in all the numbers, I get this ratio here, and I'm going to cross multiply the sine 30, and I get b equals all that stuff. And when you do that calculation properly, I get that b is equal to this. So if I have that b is equal to that long number, I can now use the red triangle to solve for h. Since I'm dealing with a 90-degree triangle, I have this angle here. According to that angle, this is the opposite side. And we have that this is the adjacent side. And the only thing that relates opposite and adjacent is the tan ratio. Plugging in all the appropriate numbers, I get tan 28 is equal to h over that long number. Now I'm going to cross multiply that long number, and I'm going to do this in one shot. So I'll do tan of 28 first, and then multiply it by 44.1351166. And this would be my final answer. Of course, it says to the nearest meter, so this would be 23 meters. And that's how Bert would do that. So it says justify your reasoning with calculations. I mean, if you had to speak about this, using words and pictures and all that, you've already used pictures and calculations. You can put point form notes on what you're actually doing and what you've actually solved. And as long as you put that in your own words, that shouldn't be a problem. Question number 5 on page 333 is pretty challenging. You got to pay very close attention to the wording. So it says, Travis and Bob were flying a hot air balloon from Beamsville to Vineland in southwestern Ontario. They decided to calculate a straight line distance to the nearest meter between the two towns. So you got to remember that here's the ground. Okay, so here's the ground right across here. I'll draw it really long, and you got to remember that Travis and Bob are flying a hot air balloon from Beamsville. So they took off in Beamsville and they're headed towards Vineland. Okay, now their hot air balloon could be anywhere at this point, and they're somewhere in the sky, and the hot air balloon is somewhere there. Now just remember, this is a three-dimensional object that I am trying to construct on a two-dimensional page. Now the hot air balloon, they tell us, is 226 meters from the ground. So from the hot air balloon to the ground, now the ground doesn't have to be somewhere on this line from B to V. The ground could be somewhere off in the distance out here. Okay, so the ground's somewhere off in the distance out here, and this is actually 226. All right, and I will call this, doesn't matter what I call this, I could say S for shadow of where the hot air balloon is. So potentially you have a triangle on the ground from Beamsville to the shadow of the hot air balloon, Beamsville to Vineland, and you have a line from Vineland to the shadow of the hot air balloon. That black triangle is actually a bird's eye view of the ground. All of those lines are on the ground right now. Now, the hot air balloon is up in the air. Okay, so I'll draw this in red. So it's somewhere up in the air. Now, they are looking down at Beamsville like this. So this is straight up and down, you got to remember. And the line from Beamsville to the shadow is a horizontal line. So, of course, these two meet at 90 degrees. Okay, now the hot air balloon is going to be looking down at Beamsville here. Okay, looking down at Beamsville like this. So there is a triangle that is formed from the hot air balloon to the shadow of the hot air balloon, and to Beamsville, okay? So the black triangle is all on the ground, and this red triangle is in mid-air coming out of the paper. And then also there's a triangle that is formed for the line of sight towards Vineland. Now remember, again, this line that goes from the hot air balloon down to the shadow is a vertical line. And we know that from the shadow to Vineland, that is a horizontal line. So this technically is 90 degrees, this angle there, and it's coming out of the page. Again, there is a line of sight from the hot air balloon to Vineland there, all right? So this is much like the picture of number 7 with the Romeo and Juliet and Paris, okay? Now, there are other pieces of information they give you here. They say that they measure the angle of depression from the hot air balloon to Beamsville to be 2 degrees, and from the hot air balloon to Vineland to be 3 degrees. Let's remember what the angle of depression means. So a side drawing, a side view of what's occurring here, okay, where this is Beamsville, this is the shadow, and this is the hot air balloon, okay? We have to know what angle of depression means. Angle of depression, please do not put the angle of depression 2 degrees over here. This is not the angle of depression. Angle of depression, if you take a look at the actual definition of angle of depression, an angle of depression is always from the horizontal line. So we're going to draw a horizontal line in midair to the line of sight. So this is the line of sight right here, and this is the horizontal. This right here from the horizontal to the line of sight is actually your 2 degrees. It's outside of the triangle. Now, funny enough, if you look at the definition for angle of elevation, the angle of elevation is also the same definition from the line of sight to the horizontal. So horizontal to the line of sight. If you notice in this picture, this is parallel to that. And this is a Z pattern right here. And we know the interior angles of a Z pattern are the same. That's why they have the same definition. The angle of depression is the hot air balloon looking down at the town of Beamsville, and the angle of elevation is the town of Beamsville looking up at the hot air balloon. Both are 2 degrees. Angle of elevation and angle of depression is always from the horizontal line of sight. So in actuality, in this picture, that should be labeled as your 2 degrees. Okay, not this. Please do not label that as your 2 degrees, because that is incorrect. Angle of elevation is always, and angle of depression always from the horizontal to the line of sight. Likewise, the same scenario occurs for the hot air balloon looking down at the town of Vineland. Again, if I was to draw a horizontal line, the horizontal to the line of sight, this is your 3 degrees, okay, right there. So that means this is 3 degrees. Angle of elevation and angle of depression is always from the horizontal to the line of sight, okay? So whether it is the hot air balloon looking down at the city of Vineland or Vineland looking up at the hot air balloon, they're both 3 degrees. Then it says also that they measured the angle between the lines of sight to the towns as 80 degrees. So all they're saying is the lines between the towns is 80 degrees. So we have that this, where the S was, this much right here is your 80 degrees right there. Okay, and you are trying to calculate the distance between, I guess, Beamsville and Vineland. So is there enough information? So let's try to calculate this. So we're trying to figure out what this D is from this distance from here all the way to here. I mean, that would be easier to find if I had other information of that black triangle. Okay, and I can find information of the black triangle because if I take a look at the blue triangle, I can figure out this side using that blue triangle. I'll call that X. And if I look at the red triangle, I can figure out this side of the red triangle. I'll call that Y. So I'll find those two things first and see if that helps me. So I've drawn the red triangle, and according to the triangle, this is 2 degrees. They're giving me 226, and I'm trying to figure out y. Opposite and adjacent, tan is the only thing that relates these. So using tan to solve for y, I end up with tan of 2 is equal to 226 over y. Cross multiply and divide out the y with the tan of 2. And I get that y is equal to 226 all over tan of 2. And of course, keeping all decimals, I get that this is equal to y. Doing the same thing for x, I'm going to end up with tan of 3 is equal to 226 over x. Cross multiply the x and divide out the tan of 3. And I end up with x is equal to 226 over tan of 3. And solving for x, I get that x is equal to 4,312.336891. Now, I have those two pieces of information, so I'm going to erase a lot of this picture here and only leave the black triangle just so you can see how we're going to solve for D. And you end up with these measurements here. So you have that this is a triangle that has 80 degrees. You have this side length here, you have this side length here, and you're trying to figure out D. Now there's no 90 degrees, so obviously the only thing you can turn to is either the sine law or cosine law. In this particular case, you're going to turn to the cosine law because the cosine law always is used if you have two side lengths and the angle in between the side lengths, right? And the way the cosine law is written is a squared is equal to b squared plus c squared. It's almost like the Pythagorean theorem, minus this 2bc cos of a. Now, of course, this is not triangle ABC. This is triangle, this side length over here is called B. This side is called V, and this side was called S, or maybe you want to call it D for now since this is little d. The way you would arrange these letters, since you're looking for little d, it would be written like this, d squared over here, and then all the other letters. B squared plus V squared minus 2bv cos of, and of course it is going to be big D. So I'll let you finish this problem on your own, but that is what you're going to plug in all the numbers into the right side of this equation and then figure out D after you've done all the proper math here. So let's take a look at question 13 on page 339 from the review. It says, while standing at the left corner of the schoolyard in front of her school, Susie estimates that the front face is 8.9 meters wide. So the front face of the school, I have it written in red, drawn in red. We have, this is 8.9 meters wide and 4.7 meters high. So we have the height of this school face to be 4.7 and the width to be 8.9 meters. Now Susie is standing somewhere on the left yard, okay, left of the schoolyard. So somewhere out in front of the schoolyard in the left, okay. And she can obviously see the top of the building, the bottom of the building. She sees the entire face of the school. It says here that from her position, Susie is 12 meters from the base of the right exterior wall. Okay, so this is the base of the right exterior wall. So this is Susie. This is the base of the right exterior wall. And from Susie to the base of the right exterior wall, they say this is 12 meters. Okay, so that's 12 meters. And it also says she determines that the left and right position or exterior walls appear to be 39 degrees apart. So that was the right base of the wall, and this is the left base of the wall. Call that L. And we know that looking at the left and looking at the right, between the left and the right, they're saying that this measurement here is 39 degrees. Okay, so we'll put 39 degrees in here. Then it asks from her position, what is the angle of elevation to the top of the left exterior wall? So this is her position, and this is the top of the left exterior wall. So the angle of elevation, remember, is always from the horizontal to line of sight. Remember that the blue triangle that you see here, okay, from S all the way to R, all the way to L, that blue triangle there, all of that triangle is a bird's eye view. Every single one of those lines are on the ground. Now with this black triangle, you can see that we have 4.7 as the height of the school building that goes straight up and down. We have this from S to L, which is on the ground, and we have this from S to T. Now, this has to be a 90-degree triangle sticking out of the page because you have the side of the building that goes straight up and down, and from S to L is the ground. So that's going to meet at 90 degrees, a vertical line and a horizontal line. Now, the angle of elevation is always from the horizontal to the line of sight. The horizontal line is S to L. The line of sight is S to T. So this is what we're after. What is this angle of elevation right there? So I've decided to break up both triangles here. So if you take a look at the black triangle first, it's a 90-degree triangle, and they're giving us that this is 4.7 meters. But it is impossible to find theta unless we're given another measurement. So looking at the overall picture, I mean, we don't have another measurement, but if we look at S to L, that is in common with the blue triangle from S to L. So we could technically, if we found this S to L in the blue triangle, which is the same as the S to L in the black triangle, this question would be complete right now. So that's what we're actually going to do. Before we figure out that angle of elevation, we're going to have to figure out that length from S to L using the blue triangle. So how are we going to do that? So let's look at triangle number 2 and let's see what we're given. This second triangle here, we are given that this is 39 degrees. We're given that this is 12 meters. We're given this is 8.9 meters. And that's it. There's no 90-degree triangle. This is not a 90-degree triangle, so please don't go using Pythagorean theorem. Please don't go using SOHCAHTOA, aka trig ratios, because you cannot use trig ratios for this triangle. You can only use the sine law or the cosine law. So the way this is set up right now, if we take a look at this, we have 39, and we also have its opposite side of 8.9. We also have the 12 here for one of the side lengths. We can definitely figure out the opposite angle right here. So if I go to figure that out, I can use the sine law if I write this down correctly. Okay, so we could figure out that, and that's all we could figure out right now. From there, maybe we can use that information to figure out more information, but that's the way the problem is set up right now. We're given two side lengths and the angle opposite one of the side lengths. So if I set this up, the only thing I could possibly do right now is find the angle L. So I'll set this up with the proper sine ratio. So I wrote sine L over little l equals sine S over little s. I wrote the angles up top because I'm looking for the angle L. I can't find r or little r right now, so I'm going to fill in the blanks here. So I end up with this, and I'm going to cross multiply the 12, and then calculating this properly, I get that sine theta is equal to positive 0.8 48521,876. Now, before we get ahead of ourselves, we have to remember the cast rule, okay? We always have to remember the cast rule because whenever we use the sine law, we have to remember that there are two answers when sine of an angle equals a positive number. There are two possible values for that angle L. There's the acute answer and there's also the obtuse answer. So if we actually go about our business the same way and solve for this, and we solve for both answers, we have to solve for both, and we do the sine inverse of this decimal, I get that L is equal to approximately 58 degrees. Now you shouldn't round this answer, I'm just rounding this answer so it just looks easier, but L is 58 degrees. That's one of the answers. The other answer you have to remember is the obtuse side of it, which is 180 minus 58. This is part of your sine law, the ambiguous case lesson, so you can look back at that. And you end up with 122 degrees as your second answer. Now, of course, you cannot have two answers in a real life word problem. So which answer makes sense? So majority of the time, it would be the acute answer that makes sense. But if you take a look at the picture, if Susie is somewhere on the left side of that building, okay, and this angle over here, this angle L, we can tell clearly the way that it's drawn. If she's in the left side of that schoolyard, that angle has to be an angle that's bigger than 90, okay? It's not drawn to scale, of course, but it has to be bigger than 90 in order for this to make sense. So the answer cannot be 58. The correct answer has to be 122. So this is where this question could get tricky for a lot of people. So this is where somebody may have made a mistake. So 122 is the correct answer for L. Now that we have L, I'm going to find R very easily because angle R, we understand that all the angles add up to 180 degrees. So angle R is just going to be 180 minus 122 minus 39. And so angle R is going to be equal to 19 degrees. Okay? Remember, the whole reason for even doing this is to figure out the distance that these things share in common, the L to S, okay? The S to L is very, very, very important because those two triangles share that in common, okay? So now I can find that S to L by using the sine law again. So I've erased all this stuff and I can rewrite this sine law as little r over sine of big R is equal to, let's say, little s over sine of big S. It doesn't matter which one you use. Now remember, this was a rounded answer. You shouldn't actually have rounded the 122 and all that, but I did just for the sake of showing you this a little quicker. Now, if I plug in the correct variables, notice I put the lowercase letters up top because I'm trying to figure out little r, so it's more appropriate this way. So I end up with this here, and so I am going to cross multiply the sine of 19, and I get that little r is equal to all this. And of course, I should probably keep as many decimal places as possible, but for sake of argument, let's keep just a couple of decimal places. R is equal to 4.60. So we know the distance from S to L is 4.60. So this is 4.6. There is enough information now here to figure out the angle of elevation theta. So now I can figure out theta very easily because with this 90-degree triangle, I can use trig ratios. According to that angle, this 4.7 is the opposite side, and this 4.6 is the adjacent side. The only thing that relates opposite and adjacent is tan. So I know that tan theta is whatever the opposite side all over the adjacent side. Filling in the blanks, we end up with this. And obviously taking the tan inverse of this number here, so I'll just put tan inverse of the answer. When I do the tan inverse of this, I end up with, when I round this properly to the nearest degree, as your book says, I end up with 46 degrees. Now, it's very important that we don't ever round until the very end. I know I've rounded in this question, but sometimes rounding an answer and finding another answer, rounding that answer to find another answer and rounding that answer ends up messing up your final answer by a degree. So you got to make sure that the only thing you actually round is the final answer. Everything else, you should be keeping full decimal places for everything. Well, sadly, my time has come to an end. I'm sure you enjoyed some of those challenging trigonometry problems. Be sure to look at my Unit 5 mid-chapter review for help evaluating trig ratios from
0 to 100.
Oh, not 0 to 100. It's 0 to
360 with the wrist, boy.
That's right. Hopefully this video brought to you by Explain Everything was helpful. Leave your comments below. I'm the math coach saying thanks for watching and see you next time.